very happy to be here and very thankful to be here and learn many new things. And today I'm going to talk about some work on the Zeta function and the Casimir Effect and Analytic Surgery. So I guess I'll start off with the definition of analytic surgery, which I stole from Matteo and Melrose's GAFA paper in 1995. This is where the term analytic surgery came. So it corresponds to a degeneration of the metric to an exact B metric across an embedded hypersurface. So what's going to happen is they take a manifold and then they're going to basically try to separate it by degenerating the metric on it. So I'll just, so instead of reading it, I'll just show you graphically what's happening. Okay, so this is with Matteo. I'm sorry? Oh, sure. I can't. Let's see. I guess I could. Okay. Okay, so they look at a closed, a smooth, compact manifold, and say that you have a hypersurface that divides it, and for epsilon greater than 0, they're going to consider a metric g epsilon, dx squared over x squared plus epsilon squared plus h, where here x is a defining function for the separating hypersurface, y, and h here is a metric on the cross-section, y. And then what they're going to do is, what they did in this paper is they analyze something called the eta invariant, which I won't talk about today, but it's a very important invariant. They study the behavior of the eta invariant as epsilon goes to 0. So what happens as epsilon goes to 0 is we get this degenerate metric there, dx squared plus x squared, dx squared over x squared plus h, which is actually a metric which gives the geometry of a cylindrical end. And it's called a B metric. And but we're actually going to not do analytic surgery in this sense. We're actually going to do analytic surgery in a different sense. So we're going to consider a closed manifold, well actually more generally manifold with boundary or even corners. And let's say that you have a dividing hypersurface y. And instead of using a metric to somehow stretch the manifold, we're just going to physically stretch it. So we're just going to cut the manifold there at y, stick in a cylinder, and then say of length 2r, and we're going to let r go to infinity. And then we're going to try to study what happens to certain objects on such manifolds. And what happens is when you get to r equals infinity, you could think of it as somehow taking your manifold and breaking it into two of them, each of which has a cylindrical end on it. And analytic surgery seeks to understand how certain spectral objects, and we're going to be focusing on the zeta function, how they behave under this surgery. Okay, so this type of surgery was, I think, first considered by Douglas and Wojciechowski back in 1991, and then subsequently by other people. In the case where, instead of having a manifold where you actually stretch it, we consider a manifold boundary, and you sort of just elongate the boundary. And then later on, by more people, they studied the situation where they actually stick a cylinder in a closed manifold and then stretch the cylinder apart. So let's see. So what we're going to do is we're going to look at first the Casimir effect. So this is sort of what motivates this whole study here. And then we're going to look at what are zeta functions, so what are these objects I mentioned already. And then talk about the behavior of zeta functions under analytic surgery. And then at the end, we're going to go back to the Casimir effect and then see how some of these ideas apply to it. Okay, so first of all, what is this Casimir effect? And we're going to see how Casimir, when he computes this energy that I'm going to talk about, it actually involves exactly this stretching that we're discussing. And again, the types of stretchings that we're going to be considered are exactly found in his 1948 paper. Okay, so here's Casimir. And in 1948, he published an amazing paper. It's just 3 pages. I have it on my computer, on the attraction between two perfectly conducting plates. So basically, he proved the existence of energy from nowhere. So he showed that in a vacuum, you take 2 parallel plates and put them close to each other, they're going to start attracting. So it's quite an amazing sort of theory. And so let's see. So here, this is your parallel plates here. And let's say that the distance between them is a. So you have two parallel plates. The distance is a. And how does he compute the energy between these two parallel plates? Well, in quantum mechanics, basically you could somehow identify energies with eigenvalues of the Laplace operator. And so the eigenvalues represent somehow these eigenvalue of the wave function corresponds somehow to the energy of the wave function. So to find the energy between the plates, what you have to do is you have to find the eigenvalues of the Laplacian. So here we're in R3. And what we're going to do is we're going to find the eigenvalues of the Laplacian, and then we're going to add them all together. And that'll give us our total energy between these plates. Okay, so let's see. So we have two parallel plates. The distance is a between them. Here are your wave functions right there. Oh yes, we put Dirichlet conditions on the plates. So you have sine of pi nz over a times z. And z here is the coordinate going into the board. Okay, so those are your wave functions, and the corresponding eigenvalues are these guys here. The kx squared plus ky squared plus nz squared, pi squared over a squared. Take the square root of them, and remember you're supposed to sum them. Unfortunately, this sum is kind of nonsense because, first of all, these kx and ky's are real numbers, and you're summing over all integers, so this sum actually makes no sense whatsoever. So this is what Casimir does. He says, well, instead of considering two parallel plates of infinite extent, let's go ahead and consider a parallel plate of side length L. And here I just stole this I took a picture of this part of his paper. So what he says is the possible vibrations of the cavity defined by x between 0 and L, y between 0 and L, and z between 0 and z is going into the board. And here are your wave numbers, pi nx over L. Remember, you're taking Dirichlet conditions. And then, so those are and here are your eigenvalues of the Laplacian, kx squared plus ky squared plus kz squared. Take the square root, and then you add them all together, and that's the energy of this system here. And then what Casimir wants to do is he wants to take L to go to infinity to get two infinite parallel plates. But of course, here you're summing integers, and this sum actually makes no sense whatsoever because you have infinitely many of these positive integers there. Okay, so let's just kind of look at what Casimir does. He wants to compute the energy between these two infinite parallel plates. So what he does, he truncates these plates, side length L, and he computes the energy for this finite guy, and then takes L to go to infinity to get what he wants. Okay, so how does, so he deals with this sum of the square roots of the eigenvalues of the Laplacian, and by some formal reasoning, he in fact says E sub L is equal to the area of M sub L, or it's actually equal to, times a constant. So I guess what I said is not quite true. He said E sub L is L squared times a constant, but L squared is basically half the area of M sub L. Okay, and then what he computes is this energy is, he finds E sub L divided by the area of M sub L. M sub L is, again, just the two parallel plates, but only a side length L. And then he computes this limit here, and he gets negative 1 over 12 pi times 120, all that times pi over a cubed. And of course, this energy is not zero. And you could find, from this energy, you could find the force between the plates. And here's his conclusion. So he says, okay, there exists a force between two metal plates which is independent of the material of the plates as long as the distance is so large, and so on and so forth. And then at the end here he says, although the effect is small, and it's actually small because I left out Planck's constant, so you actually have Planck's constant multiplying that, an experimental confirmation seems not infeasible and might be of a certain interest. And this was back in 1948. And almost immediately, this Marcus Sparnay, in 1950, he tried to experimentally verify this energy from nowhere, but it was non-conclusive. And then finally, in 1994, I guess you could say it was first verified, I guess to within 20%. And just one little remark here is that Casimir told Pauli about this energy from nowhere, and somehow Pauli's response was that it was absolute nonsense. But actually, as we said, it's been experimentally verified that indeed we do have these forces that somehow pop up from nowhere. Okay, so somehow we want to contribute to Casimir's program, and how are we going to do that? Well, we could try to do it in several ways. So here is Casimir's formula here for the energy between two parallel plates of infinite extent. And we're going to try to just maybe try to see where do these numbers come from? Like, where 120, why is that there? Pi over a cubed. Somehow these constants seem like, okay, they're nice, but we sort of want to understand where do they originate from. And we also want to understand somehow if we could put Casimir, this is basically an example he gives, where he somehow takes two finite plates and takes them go to infinity. And somehow we want to give a framework under which, Casimir's computation is just an example or a special case of a general theory. And this general theory is going to be analytic surgery. And what types of analytic surgeries are we interested in? Well, let's go ahead and take Casimir's finite box. And again, what we want to do is we want to be able to take the sides of this box and make them go off to infinity. Okay, so how are we going to do that? Well, you could call the side length L, but for purposes of generalization, let's go ahead and do the following. Let's take his box, and let's go ahead and take other boxes, say of side length R, and attach them to the one to the right, one to the bottom, and then one in the corner there. And then we're going to take R to go to infinity. This basically has the same effect as what Casimir did. In R equals infinity, we get two infinite parallel plates, just as Casimir did. And what we want to do is we want to understand how this Casimir energy behaves on M sub R. Okay, so we see that example of Casimir's box is really can really be generalized to manifolds. So here's a situation. Let's consider a manifold with corners of codimension 3. So this is... Okay. Yeah, so here's a manifold with corners of codimension 3. Let's pick two hypersurfaces, just like in Casimir's box. So let's go ahead and take the bottom hypersurface and the right hypersurface. And what are we going to do? Let's do exactly essentially what Casimir did. Let's stick on a cylinder, okay, say of length R to the right of it. Okay, stick on a cylinder here on the bottom of length R. This is not proportional, of course, but allowed me to draw it. Okay, now what we're going to do is we're going to somehow compute Casimir energies of objects like this, and then take R to go to infinity. Okay, and this general setup would contain Casimir's setup as a special case. And then what happens is we get a manifold of infinite extent, just like Casimir's two parallel plates. And again, the goal of this whole project is to somehow understand Casimir energies and how they change with R. Okay, there's another way we could somehow copy Casimir's sort of idea here, and it's as follows. So instead of attaching cylinders to the hypersurfaces, so we have this solid box here, instead of attaching cylinders, let's do the following. Let's go ahead and take his box and let's cut it, say in half. So basically we're going to do what was in the Matteo-Melrose paper. And then now let's go ahead and take this box here, and then let's stick in a cylinder of length 2R, okay, from negative R to R, and then cross, of course, and then cross the cross section. Okay, so you stick in a cylinder of length 2R. Now let's stick in another cylinder of length R to the bottom of that. And now let's take R to go to infinity, and you can see this exactly does the same thing. It makes it go R to infinity this way and R to go to infinity down. You get, again, two parallel plates of infinite extent. So let's go ahead so as R goes to infinity, you could think of it as what we talked about before in analytic surgery. You could think of your manifold as somehow separating into two separate ones. And the proper setting for these types of problems are the following. So let's consider now a manifold with corners, and let's take a hypersurface that divides it, and let's do exactly the same thing as we did with Casimir's box. Okay, so here's your manifold with corners. You have a dividing hypersurface. let's go ahead and stick in a cylinder of length 2r in between them. So it's really negative RR cross the cross section. Stick that in there. Okay, that stretches your manifold by 2r horizontally. And now let's stick on a cylinder on the bottom of length r. And then let r go to infinity. And then you get somehow two manifolds of infinite extent, in some sense. Okay, so anyways, this is sort of the program. Okay, so let's summarize. So in 1948, Casimir showed that there's some energy between two parallel plates, even though the parallel plates are in a vacuum. And here's his formula for the Casimir energy. Okay, which again is, what you do is you find the eigenvalues of your system, and then you take their square roots and you sum them. Okay, and what he did was he did this by, he found this formula by performing analytic surgery on a manifold with corners of codimension 3, namely this box. Okay, and remember, you had Dirichlet conditions inside, so it's a solid box with Dirichlet conditions on the sides of it. Okay, and it's experimentally verified. So let's see. What we're going to do now is we're going to try to understand Casimir's idea of taking the eigenvalues, taking their square roots and summing them, and that's zeta functions. Okay, so a zeta function is basically a generalization of the Riemann zeta function. And these zeta functions are actually meromorphic functions, and somehow they encode lots of information about the underlying space. But most importantly for this talk is that these zeta functions, you can use them to give a rigorous definition of the sum of the square roots of the eigenvalues. Okay, so I'm sort of not assuming that anybody knows about zeta functions here. So let's go ahead and talk about the definition of a zeta function. So let delta be a Laplace type operator on a compact Riemannian manifold. And let lambda 1, lambda 2, and so forth be the eigenvalues. Oh, if the manifold has boundary, we always put Dirichlet conditions on the sides. And then for complex number S, the zeta function is defined in this way. So what you do is you take the eigenvalues of your Laplace operator, delta, and you take to the power negative s, and you sum over all eigenvalues. And of course, that sum, this is well defined, provided, of course, that sum converges. So let's look at an example real quick. Let's go ahead and look at negative dz squared on an interval 0a. So the interval 0a is exactly, say, the corner of Casimir's box. Okay, so it's exactly a segment of length a. And you have Dirichlet conditions on the ends of it. The eigenvalues are n pi over a squared, and the corresponding eigenvectors are sine n pi over az. Okay, so let's go ahead and compute since we know all the eigenvalues of that Laplacian on the segment, we could compute its zeta function. So here it is by definition, sum over all lambda k's to the power negative s. And of course, all these eigenvalues are positive. So that's just a sum from n equals 1 to infinity of n pi over a to the negative 2s. And you could take out the pi over a to the negative 2s. And what you end up is pi over a to the negative 2s times the zeta function, the Riemann zeta function of 2s, because the Riemann zeta function is defined as the sum of the positive integers to the negative s. Okay, so here we see that this operator here on a segment, the segment of Casimir's box, say a corner of Casimir's box, the zeta function of that operator is related to the Riemann zeta function of complex analysis. Okay, so there's the formula again, pi over a times to the negative 2s, the Riemann zeta function at 2s. Thomas, I forgot, what time do I have to stop? Okay, so let's go ahead and try to, so therefore, since we know that explicit formula for the Riemann zeta function on this segment 0 to a, in terms of the Riemann zeta function, we could understand the properties of this zeta function of that Laplacian. And because we know a lot about the Riemann zeta function, in particular, we know that this infinite series here, the Riemann zeta function here, we know that's defined as long as the power negative s, so as long as the real part of s is bigger than 1, and this defines an analytic function on the half plane, the real part of s bigger than 1, and you could actually meromorphically continue it to the entire complex plane, except it has a pole at s equals 1, has residue 1 there. And s equals 1 is because you basically get the harmonic series. So in particular, so there's our formula for the Riemann zeta the zeta function of the Laplace operator on that segment 0 to a. We conclude that the zeta function of that Laplace operator, it extends from the real part of s. Oh, whoops, that's a mistake there. Real part of s bigger than a half, because we have the Riemann zeta function is that entire function, pi over a to negative 2s times zeta function at 2s. So it actually extends meromorphically from the real part of s bigger than a half to be a meromorphic function on the whole complex plane, except it has a pole at 1/2. And these numbers are important. So 2 is because the operator is of second order, and 1 is because you have a one-dimensional segment. And this property of the zeta function of a segment extends in great generality. Okay, so given any Laplace type operator, delta, the zeta function is defined in this way as stated before. And that sum converges for the real part of s bigger than m over 2, where m is the dimension of the underlying manifold. Okay, so this sum actually converges as long as s is over here. But you could actually extend it past that line there, m over 2, the real part of s equals m over 2. You could meromorphically extend it to the whole complex plane. Happens to be regular at 0 and actually at negative integers too, but it could have possible simple poles at m over 2, m minus 1 over 2, and so forth. Some of them are actually not poles, but this theorem holds for any Laplace type operator. In fact, okay, and this Riemann zeta function actually it actually can be used to study the manifold. So here's a very famous theorem. Okay, so it was made famous more or less in a paper, Can One Hear the Shape of a Drum by Mark Kack. It says for the Laplacian, so the true Laplacian, delta G, associated to Riemannian metric G, has this property here. So zeta tilde of the Laplacian sub G of s is just the gamma function, gamma of s times the zeta function of the Laplacian. So whenever I put a tilde, it always means take your zeta function and multiply it by gamma, because somehow that, in some sense, is the right object. These gamma factors always are troublesome in this business. But anyways, the zeta function of the Laplacian associated to Riemannian metric has this property here. So it has a pole at m over 2, and the residue is volume of m. Okay, it has a pole at m minus 1 over 2. The pole here is square root of pi, the volume of the boundary of m divided by 2. Okay, and then so on and so forth. Here it has a pole at m minus 2 over 2, where the residue there is related to the total scalar curvature of your manifold. So somehow the residues of the poles of your zeta function somehow encode geometric information when the Laplace type operator is the Laplacian. You could also use the zeta function to do other things. For example, you could use the zeta function to define something called the determinant of an operator. So take a Laplace type operator, delta. The determinant is by definition the product of all the eigenvalues. Or you could say the logarithm of the determinant is by definition the sum of the logarithms of the eigenvalues. Unfortunately, this definition is really not a definition because it's ill-defined, because, for example, these eigenvalues actually go up to infinity. I mean, n pi over a squared, for example. So you can't define the determinant in this way, but you can define the determinant using zeta functions. So this is a famous trick by Ray and Singer back in 1971. They published this very famous paper where they introduced determinants of operators. So here you have, okay, so remember the log of the determinant is supposed to be by definition the sum of the logarithms of the eigenvalues. And the thing to notice is that, well, the logarithm of lambda n, that's exactly the negative derivative with respect to s of lambda m to the negative s. Oh, so it's really just negative the derivative of the zeta function. Okay, so in other words, the logarithm of the determinant is you take the zeta function of your operator and you take its derivative and multiply by -1 at s equals 0. And actually, this the zeta function, remember, actually doesn't have a pole at s equals 0. So this is actually a true derivative. And the right-hand side is perfectly well-defined. Okay, so again, remember what you do is you have the zeta function, you extend it meromorphically to the whole complex plane, and it happens to be regular at 0. And you take the derivative of the analytically continued zeta function at 0, and you multiply by -1. And take its exponential, and that gives you the determinant of the Laplacian by definition. Okay, so that's a cool thing the zeta function can do. But what's the subject of this talk is the Casimir energy. So the zeta function can help you define the Casimir energy. So recall that the Casimir energy is defined, so you take the eigenvalues of your system, take their radicals, and sum over all of them. And that somehow represents the total energy of your system. And of course, you know, that left-hand side there is complete nonsense. But the thing to notice is that it's nothing but the zeta function at -1/2. So the sum of the radicals of the eigenvalues is exactly just the zeta function at s equals -1/2. And the right-hand side can be defined. Of course, the zeta function may have a pole at -1/2, but even if it does, it's not a worry. Just subtract off the pole, and then you have a function which is actually defined at -1/2, and just plug in -1/2 into that function. And that defines the Casimir energy. So this is a very precise definition now. So if you have a system, you have the Laplacian of that system, you find its zeta function, and then you plug in -1/2 into the zeta function, and you get a number. And again, if the zeta function happened to have a pole at -1/2, you just get rid of the pole and just plug in -1/2 into the remainder. And then that defines the Casimir energy in a very, very precise way. Okay, so what we've learned here is that the zeta function, it somehow organizes the spectrum in a very nice way. So you have the spectrum, which you have all these eigenvalues, and what you do is you pack them into one function. And this function is quite remarkable. You can use this function to try to, for example, understand the geometry of your manifold, or or for example, to define determinants of operators. And at least for the purposes of this talk, it allows you to define the Casimir energy of a system given by some operator delta. Okay, and one thing that I'll need later on is zeta functions. You can also define them. So here are the manifolds we've been dealing with. They're compact, so you have these. You have countably many eigenvalues, but zeta functions can also be defined for certain non-compact manifolds, and I'll need that later. These, for example, so-called B zeta function. But anyways. Okay, so what we're going to do now is we're going to study analytic surgery, but not in the generality that Casimir did. So remember, Casimir, he had a manifold with corners, and he started sticking on cylinders, more or less, filling in what remained, and then he took everything to go to infinity. But that's actually kind of hard, so I'll talk about that later. So we're going to talk about analytic surgery, but in an easier situation. And okay, then I said earlier, analytic surgery deals with sort of analyzing what happens to, for example, the zeta function when you stretch the manifold. And we're going to study two types of stretches before, when you have, say, a boundary and you stretch that, or you have a manifold and you cut it and you stretch it that way. So elongation and separation. So let's consider a Laplace type operator on a manifold with corners of codimension 2. And remember, everything is, we're going to assume Dirichlet. We're going to put Dirichlet conditions. And to make analysis easier, let's assume product type structures near the faces. So for example, let's call this face H0. And we'll assume that, say, that near H0, the manifold looks like -1 cross 0. -1, 0 cross H0, where H0 is a manifold with boundary. In this case, H0 is just a disk. And assume that the Laplace type operator is very nice, so it's just a product, okay, or a sum of derivatives in X plus a Laplace type operator on the cross section H0. Okay, what we're going to do is we're going to attach a cylinder there to that manifold, say of length R. And we're assuming product type structure, so the Laplace operator, it extends in a very natural way to this manifold, elongated manifold. And what we're interested in is what happens to, so remember, whenever you put tildes, it just means multiply by the gamma function. We're going to try to understand what happens to the zeta function on the manifold m sub r, and you let r go to infinity. And what we're really interested in is, okay, not just going to r equals, it goes to infinity like in sort of one dimension like this, but in 2 dimensions. But that'll be later on. We're sort of interested in what happens at s equals -1/2. Okay, well, here's the answer. Here's what happens. So the zeta function on m sub r, that manifold where you stuck on a cylinder of length r, it turns out to equal r divided by 2 radical pi and this zeta tilde of, so delta sub y is, so I don't know why in the previous slide I called it h naught, but here y is the cross section on the cylinder. The zeta function of that at s equals -1/2, or sorry, at the value s minus 1/2. So as r goes to infinity, the zeta function it sort of grows with the length of the cylinder, and then plus the zeta function on this manifold here, delta infinity. On this manifold, which we'll call it m infinity. Okay, plus the zeta function of delta infinity, which lives on this manifold m sub infinity. Okay, minus again the zeta function on the cross section. Call this cross section y. And here we have to make an assumption that this operator delta infinity, we have Dirichlet conditions here on the boundary. Okay, we assume that operator is invertible. So in particular, that implies necessarily that the operator there on the cross section is invertible. Okay, so I want to just what does that triple bar mean? Well, that triple bar means, okay, this is an equality in the sense of meromorphic functions, and to be precise, let's go ahead and define f of r comma s to be the left-hand side minus that right-hand side we had in the previous equation there. Then that triple bar meant that there exists an r naught greater than 0 such that that function f of r comma s is going to be an entire function in s. It's going to be a smooth function in r for r bigger than r naught. And I should have stated it here. Smooth in r bigger than r naught. And f of r comma s, it actually goes to 0 exponentially fast as r goes to infinity. Where exponentially fast means in the topology of entire functions. Okay, so it goes to 0 sort of on compact subsets of the complex, for S in compact subsets in the complex plane. And it actually decays exponentially. Okay, so here we have this formula here which describes the zeta function on a manifold where you're stuck on a cylinder of length r, and it describes how it grows as r goes to infinity, and there's the formula there. So it's basically equal to the right-hand side plus something that decays exponentially. And here's a corollary of this formula. So remember that the determinant it's obtained by differentiating the zeta function, and you plug in 0. So actually and multiply by -1, and then you take the exponential of that. But so here you have a formula there, and you could take the derivative of that, and you have to watch out for these gamma factors. But in any case, when you do that, you get this formula here for the behavior of the determinant of the Laplace operator on this manifold with the cylinder of length r stuck onto it as r goes to infinity. And so here's the formula. So the determinant of the Laplacian, when you multiply that by that factor there, where this psi is defined in this way in terms of the zeta function of, whoops, so that's a mistake. It's supposed to be s minus 1/2. And you multiply e to the r over 2 psi prime of 0, and that combination there is actually approaches that number there on the right. The determinant of the cross-section Laplacian times the determinant of the operator on the whole manifold, m infinity. This was first proved by Lee and Mueller, but they didn't prove it using the zeta function. They actually proved it sort of strictly working with the determinant. And here's another corollary. So remember that the Casimir energy is just the zeta function at -1/2. So here we have a formula for what happens to the zeta function as you increase the cylinder, as you make r go to infinity. So we can see what happens to the Casimir energy. Well, let's see here. So the area of M sub r, let's call this M sub r, it's basically proportional to r. Okay, so this is just a compact part. So the area, the volume of its boundary is basically, it's basically r times the volume of the boundary of y. Okay, so basically M sub r is basically r times the boundary of y plus lower order terms. So you take this formula here, divide by the area of M sub r, and you get this constant there. So in any case, you can plug in s equals negative 1/2, and that'll tell you exactly how the Casimir energy changes as you let r go to infinity. Thomas, do I? Almost 15 minutes, okay. Okay, so that was elongation, where you took a compact manifold and you stuck on a cylinder. And you could also do this other method where, okay, let's consider a manifold with boundary and take a hypersurface that divides it. Okay, call that hypersurface y. Okay, and then replace y by a cylinder negative r comma r cross y. So basically what you're doing is you're cutting your manifold, you're separating it, and sticking in a cylinder of length 2r. And you could ask the same exact question. So this is a nice manifold here with boundary. You put on Dirichlet conditions. Assume you have a Laplace type operator with, and you could look at its zeta function. And you could ask, well, what happens to the zeta function as r goes to infinity? And you get a very, very similar formula to the formula we had before. So what happens is, up to an exponentially decreasing term, that zeta function as r goes to infinity basically grows linearly with the cylinder. So it's r times r divided by radical pi, and you get this zeta function of the cross section Laplacian at s minus 1/2, and then plus a constant term, and the constant term is exactly the zeta function on, say, m1 infinity, which is you take the left half of your manifold, stick on an infinite cylindrical end, okay, plus the zeta function on, say, m2 infinity, which is the right half manifold, stuck on with an infinite cylinder stuck onto that. So somehow the zeta function splits into the zeta functions of these two manifolds, plus a term which grows in r. So here's an application. So from this formula here, you could say, well, okay, let's go ahead and take the determinant of the Laplacian, or the Laplace operator on your manifold M sub r, which is, you remember, your original manifold with a cylinder of length 2r stuck in between. And then you multiply by this factor here, e to the r at psi prime of 0, where here's psi. And then what happens is that function there of r, as you let r go to infinity, approaches exactly the product of the determinants on these two manifolds here with cylindrical ends. Okay, so somehow the determinant sort of splits. And this was first proved in 2005 by Yuan Li and by Werner Müller and Joan Müller in 2006. And of course, you could also do a Casimir. You could try to see what happens to the Casimir energy. So, and again, from this formula here, you could divide by the area of M sub r, so just the volume of its boundary, and you could see it's basically 2r times the volume of the boundary of y. Okay, more or less up to a lower order term, and so you take your zeta function here, divide by the area of 2r, and you get that guy. You get that constant there, or that function of s. And if you want the Casimir energy, just go ahead and plug in s equals negative 1/2 there.
So, excuse me.
Yes, great.
You can't, right? Because you have a gamma of -1.
Yes, but then, but this guy here, yeah, but let's see. You take the regular value. Yeah, so remember, whenever you have a pole, you take the regular value of what's. Yeah, so even this guy here, you have to take the regular value of this guy too. So it's technically not plugging it in. Did I answer your question? Or? Okay, so let's go ahead and summarize what we talked about. You have a manifold here, corners of codimension 2. You stick on an infinite cylinder, and you say, what happens to the Laplacian on that manifold as you let r go to infinity, and you see what happens to the zeta function. And you, sure. Mm-hmm. Yeah, but remember you have poles on both sides.
You wouldn't have the regular part. You just have you'd be looking at the residue, not at the regular part of the subtract the residue. Then you say if you go to the actual value where you have a pole, you take the value that's left over after you remove the residue, and that seems to be, it seems that you get some discontinuities out of that.
Does anybody have a comment about that? Yeah, maybe we could.
If you're canceling, if you can't. No, I did. Never mind.
Okay. Okay, so this is the summary of the sort of the simple situation where we have analytic surgery, but only occurring in one dimension. And here we could get some very precise formulas. But of course, this is we didn't actually analyze the Casimir problem. We sort of cheated and just said, well, let's analyze something simpler. But let's go ahead and go back to the Casimir problem. So here, remember, he had a box of side length L, and the width here is A, and he proved this formula here. And again, what we're interested in is where do these mysterious constants that appear in this formula here, do they have some meaning? And you can already see it. Pi over A looks like sort of related to the eigenvalues of that Laplacian on a segment of length A, so maybe it's somehow related to that. And can we sort of put this in a framework? And here, this is just preliminary work and not about any paper yet. Okay, so here let delta be a Laplace type operator with Dirichlet boundary conditions over a manifold with corners of codimension 3. Okay, so here's our manifold with corners there, and we have to assume product type structures near the hypersurfaces. And so again, let's go ahead and, for example, near that hypersurface, say, let's call that H naught now. You have it's basically just a product, and the Laplace operator is just a sum of differentiation in, say, X, which is normal to H naught, and then plus the Laplacian on H naught. And then let's go ahead and assume, we have to assume these invertibility conditions, just like we assumed in the previous situation, the easier situation. Let's assume that delta M infinity is invertible. So this is M infinity is what happens when you take an infinite cylindrical end, attach it to the right, and attach a cylinder there on the bottom. So here H0 and H1 are two hypersurfaces. They intersect in actually, let's call the corner, let's call where they intersect Y, that's a manifold with boundary. So in particular, this implies invertibility conditions of certain normal operators as well. But, so invertible means Fredholm and no null space. And that assumption is actually satisfied for Casimir's problem. For example, this segment here is invertible. The Laplacian there on Y is invertible. But anyways, let's go ahead and take our compact manifold with corners. Let's attach a cylinder of length R to the right, and a cylinder of length R on the bottom. And let delta sub R denote the natural extension of the Laplace type operator delta to this new manifold. And we're interested in looking at sort of ratios of the zeta function with the area. So just a little remark now is the area of this manifold is called that M sub R. It's basically R squared times the volume of the boundary of Y. And Y here, I just want to recall what Y is. Yeah, Y here is this corner. It's a manifold with boundary. And yeah, so there we are. So the area of M sub R is R squared times the volume of the boundary of Y plus, and R squared because, well, yeah, you have two R's there, plus something of lower order. So what we're interested in is this ratio here, just like what Casimir did. Look at the zeta function divided by the area of M sub R, and we're really interested in what happens at S equals -1/2. And here is the formula here. So the limit of the zeta function divided by the area of M sub R is given, whoops, here we go. Okay. It's given by that formula right there, 1 over 4 pi, the volume of the boundary of y, s minus 1, all that times the zeta function of the zeta function of y, and y is a manifold with boundary. But before we had s minus 1/2, and now we have s minus 1. So it's basically s minus 1/2, and you're going one codimension less, so you pick up another minus 1/2, so you get s minus 1. Okay, so anyways, plug in s equals negative 1/2, and what we see is we get that the limit of this zeta function divided by the area of m sub r is negative 1 over 6 pi now, the volume of the boundary of y, the zeta function of the Laplacian of y at negative 3/2. Or, let's define this to be the Casimir energy of m infinity, and that's equal to negative 1 over 6 pi, the volume of the boundary of y, the zeta function of the corner where the two hypersurfaces intersect, which is a manifold with boundary at negative 3/2. Okay, so there's our formula for, our formula for, which is our definition of the Casimir energy of m infinity, and then as the limit of the ratio of the zeta function with the area of the manifold, and we get that formula there. So let's go ahead and apply this to Casimir's example. Okay, so here we have a box, side length of the part going in is A. Thomas, may I ask? 4 minutes? Okay. Okay, now in this case, our H naught is the right side of that box. Our H1 is the bottom side of it. And then our Y is the corner where they intersect, which is exactly a segment of segment 0A. And let's see here. So remember our formula right there on the top there. We have the zeta function of Y, but in fact, we computed that explicitly about 30 minutes ago. So the zeta function on segment 0A is exactly pi over A to the negative 2s times the zeta function, the Riemann zeta function at 2s. Okay, so in particular, the Casimir energy of two infinite parallel plates is nothing but negative 1 over 12 pi, and then make sure you plug in negative 3/2 here. Negative 1 over 12 pi times 120. Oh, and here we see the 120. So the 120 is actually the Riemann zeta function at negative 3. So that's the mysterious 120 is actually, it occurs because it's exactly the value, so 1 over 120 is exactly the value of the zeta function, the Riemann zeta function at negative 3. And then the pi over a to the power 3 is exactly because we have that factor there. So that's where those mystery numbers come in. And you could also consider what happens when you have a manifold with, since I only have a couple minutes left, I'll just kind of just go over this. We have a now manifold with corners here, and you have a dividing hypersurface, and then you could stick a cylinder in between the two manifolds and stick a cylinder on the bottom and see what happens as R goes to infinity. You basically get the same information, the same formula. So let me just go ahead and skip everything. So please don't look. And then I'll just say thank you. I'm sorry? No, that's the funny thing. So what he did was he used the Euler-Maclaurin formula. So what he did was he took the sum of the eigenvalues, and he actually changed the sum into an integral. Because I don't know if you remember the notation Casimir used was kx, ky, and those were real numbers. So he integrated over kx and ky, and he summed over n, which we had n pi over a, the eigenvalues of the segment. And then what he did is we multiply that by what's called a regulator in physics, which is basically a rapidly decreasing function. And so that made that integral now convergent. And he used the Euler-Maclaurin formula to get the leading order term of that sum. Yeah, so it's kind of impressive, actually. Yeah, what Casimir did.
Multiply e to the minus n epsilon, and then the integrals aren't hard.
Mm. Yeah, no.
Everything pops out as a epsilon.
Yeah. The dimensions?
What's A? And what are the size of the plates?
Oh, that's a very good question. I don't know. I actually,
Just to have an idea of the, when we begin to see these kinds of things.
yeah, I guess an article I read says that this Casimir energy is somehow responsible for geckos being able to walk upside down. So I guess there you could see it. But I guess it's supposed to be important in nanotechnology where you have to worry about very sensitive nanostructures hitting each other. And somehow this Casimir energy is important in that.